Good evening. I am Laura Green. I'm a member of the AAAS Board of Directors, the Chief Scientist at the National High Magnetic Field Laboratory, and a Professor of Physics at Florida State University. I am absolutely delighted to introduce Dr. Fabiola Gianotti, who will deliver a plenary lecture entitled Fundamental Research at CERN and International Collaboration. First, however, I have the pleasure of presenting two of AAAS's most distinguished awards. We will begin tonight with the AAAS Early Career Award for Public Engagement with Science. This annual award was established in 2010 to recognize early career scientists and engineers who demonstrate excellence in their contribution to public engagement with science activities. For the purposes of this award, public engagement activities are defined as the individual's active participation in efforts to engage the public in science and technology-related issues and promote meaningful dialogue between science and society. Let's learn more about this awardee's engaging work.
The AAAS Early Career Award for Public Engagement with Science recognizes early career scientists who demonstrate excellence in their public engagement with science activities. This year, we honor Monica Ramirez Andreotta, Assistant Professor of the Department of Soil, Water, and Environmental Science at the University of Arizona. She is honored for her innovative approach to engaging communities on environmental health-related problems and working collaboratively with them to research and solve these problems. Residents of disadvantaged communities in Arizona and across the nation are disproportionately affected by environmental problems like pollution, water scarcity, and food insecurity. Ramirez has been heading up citizen science programs for years in an effort to be a steward of the environment and to help these disadvantaged communities. This includes two major programs she launched, Garden Roots and Project Harvest. In addition, she's made her science culturally relevant, accessible, and responsive to these communities' concerns. She also advocates for environmental education programs in which communities, organizations, government, and academic stakeholders build meaningful partnerships and cultivate opportunities for informal science education. In her research, Ramirez focuses on the effects of exposure to environmental contaminants, with special attention on plant soil systems to improve soil, air, and water quality. And she tightly integrates her research with her outreach and public engagement efforts. Finally, her work is international as she engages communities on both sides of the US-Mexico border. In her public engagement efforts, Ramirez has been a true innovator in the ways she's promoted dialogue and collaboration between scientists and communities affected by her work. Monica Ramirez Andreotta, recipient of the 2019 AAAS Early Career Award for Public Engagement with Science.
I'm delighted to present the 2019 AAAS Early Career Award for Public Engagement with Science to Dr. Monica Ramirez Andreotta, Assistant Professor of Soil, Water, and Environmental Science at the University of Arizona. Very cool. Okay. Next, the AAAS Manny L. Baumick Award for Public Engagement with Science. This annual award was established in 1987 and recognizes scientists, engineers who make outstanding contributions to the popularization of science. Let's learn more about this year's recipient.
The AAAS Manny L. Baumick Award for Public Engagement with Science recognizes working scientists and engineers who make outstanding contributions to the popularization of science. This year, we honor Joanna Varon, Professor Emeritus of Microbiology and Head of Science Communication and Public Engagement at Manchester Metropolitan University in England. Varon is a compelling science communicator and a great champion for public engagement, as well as an excellent mentor and leader. In particular, she has developed a wide variety of ingenious public engagement activities. Those have included dining events highlighting the contributions of microorganisms to our food, and an activity that used vampires, zombies, and werewolves to illustrate how diseases spread. Recent events have focused on antimicrobial resistance, taking visitors back to the pre-antibiotic era in World War II tunnels, and in a courtroom setting where she helped develop science on trial. In that event, expert scientists were questioned about the future impact of antimicrobial resistance. She also skillfully leverages people's interest in literature and arts. Her initiatives there include a science corner at the Manchester Children's Book Festival and a Bad Bugs book club to discuss novels in which infectious disease is part of the story. As a mentor and leader, Varon has led her university's involvement in many local festivals. She shares her innovations and public engagement with academic peers. She does this through articles in peer-reviewed publications, presentations at academic conferences, advisory roles, and through learning resources distributed to hundreds of schools. She became an emeritus professor in 2018, but has continued to create innovative engagement events and publish and present research on these efforts. Joanna Varon, recipient of the 2019 AAAS Manny L. Baumick Award for Public Engagement with Science. This award has been renamed for quantum physicist Manny L. Baumick, thanks to a generous endowment he established. Baumick is internationally known for the advances he made to excimer laser technology, which eventually led to LASIK eye surgery. He hopes to elevate the recognition of working scientists for their exceptional efforts to communicate science in ways that inform and engage the public.
Thank you. It is my great pleasure to present the 2019 AAAS Manny L. Baumick Award for Public Engagement with Science to Dr. Joanna Varon of Manchester Metropolitan University. Continuing with our all-girl group, I am now very excited to introduce our headlining speaker for today. Dr. Fabiola Gianotti is the first female director of CERN, a position she assumed in January 2016. She has been a research physicist at CERN since 1994 and since 2013 an honorary professor at the University of Edinburgh. Dr. Gianotti has worked on several CERN experiments and has been involved in detector R&D, construction, software analysis, software development, and data analysis. From 2009 to 2013, Gianotti held the elected position of project leader for the ATLAS experiment and had the task of presenting the results on the search for the Higgs boson in a seminar at CERN on July 4th of 2012. Gianotti has authored or co-authored over 500 publications in peer-reviewed scientific journals and has given more than 30 invited plenary talks at major international conferences. She also holds or has held membership on several international committees, including the Scientific Advisory Board of the UN Secretary General. Dr. Gianotti is the recipient of the Special Fundamental Physics Prize of the Milner Foundation and the Enrico Fermi Prize of the Italian Physical Society, and the Medal of Honor of the Niels Bohr Institute of Copenhagen. She was included among the top 100 most influential women by The Guardian, Forbes, and ranked 5th in Time Magazine's Person of the Year in 2012. Gianotti received her Ph.D. in experimental particle physics from the University of Milan. Please join me in welcoming Dr. Fabiola Gianotti.
slides? Okay. So thank you very much. I'm very pleased to have the opportunity to give a talk in this very important and prestigious conference, and to have the chance of presenting and discussing one of the largest scientific centers in the world, CERN, the European Laboratory for Particle Physics, and I will do so by covering all its facets, from fundamental research to international collaboration and much more. I remind you that CERN is the largest laboratory for particle physics in the world. It's an intergovernmental organization based in Geneva. Our primary mission is fundamental research, and particle physics is the most fundamental of all sciences because it studies the smallest constituent of matter and of the universe. And the research at CERN over the decades has been awarded by many discoveries. The last one is the Higgs boson in 2012, and Nobel Prizes awarded to CERN scientists. Our scientific goals are extremely ambitious, and they require the development of cutting-edge instruments and technologies in several domains, from cryogenics to electronics, from superconducting magnets to the World Wide Web. So the World Wide Web is one very good example. It was developed at CERN at the end of the 80s, actually in 1989, when CERN team Berners-Lee was a CERN employee, and since then it has changed the way society accesses information. And actually this year we are going to celebrate the 30th anniversary of the web. But there are many other examples of the impact of CERN technology on society, for instance medical application, and we'll touch upon them later on. In general, fundamental research is a driver of innovation because the scientific goals are extremely ambitious, and they require really the development of cutting-edge technologies in many fields. Another important component of our mission is training tomorrow's scientists, physicists, engineers, and also education of high school students and teachers through a large number of initiatives. And last but not least, CERN is a concrete example of peaceful collaboration by attracting about 17,000 scientists from all over the world, more than 110 different nationalities. CERN was founded in 1954 thanks to the vision of great scientist, physicist, and politician, and a US physicist, Isidore Rabi, was one of the founding fathers. It was founded with a twofold goal. On one hand, to bring back scientific excellence to Europe after the war, and also to promote scientific collaboration and peaceful collaboration among European countries after the disasters of the war. Today, CERN has 22 member states from Europe, but not only, 8 associate member states, and 3 observer countries, among which the US. The budget is about 1.2 billion Swiss francs per year. Using more friendly units, I like to say that it corresponds on average to 1 cappuccino per year per European citizen. I'm saying on average because the price and the quality of the cappuccino varies significantly across Europe. So on average. Now, this budget is shared by the member state countries in proportion to their net national income. So the largest contributor is Germany, followed by the UK, France, Italy, Spain, and so on and so forth. And this budget is used to develop, operate, upgrade the scientific infrastructure, so the accelerators, the laboratories, and the detectors, etc., that the worldwide scientific community uses to do physics, to do science. And this community actually comes from all over the world. Here you can see the map of the CERN users, mainly physicists. You see in dark blue, we have something like 8,000 scientists coming from Europe, but also many scientists coming from non-member state countries in green and in red. You see actually that the US provides the largest contingent, more than 2,000 physicists. But we also scientists coming from countries that are not really at the forefront of science and technology, like Mongolia, Montenegro, Bangladesh, Azerbaijan, Oman, and so on and so forth. And some of these scientists actually come from countries that do not entertain the most romantic relations, or they are clearly in conflict, and yet at CERN they work together, animated by the same passion for science. Now, if you think that these scientists are a bit boring and elderly, you are wrong, because if you look at the age distribution of the CERN physicists, you can clearly see a peak at 27 years. I'm also here in this peak, and I will not move out of this peak for the rest of actually, about 40%, 50% of our scientists are below 35. So one important component of the CERN population is made of students and young postdoc. There is also a long tail, and we still have also some scientists at age 80 or 90 or beyond who are still active, which demonstrates that working at CERN increases the life expectation. Now, not all of this, well, perhaps let me stress also that the fraction of female scientists, so physicists and engineers or computing engineers, today is at the level of 18%. So there is still a long way to go. However, we have made a lot of progress over the past years, because when I joined CERN in 1994, 1995, we were only 8%. Now, only 10%, typically 10% of our young people, students or postdoc, remain in particle physics at the end of their studies, simply because there are not enough jobs in research, or because they want to do something else. So about 90% of them go elsewhere. Typically 50% go to the private sector, to industry, so you can see here computing, finance, consulting, engineering, etc. And the other go to the public sector, international organization, administration, etc. So our goal, actually, our mission is to prepare them not only for a career in science, but more generally for a work in society. Since we have many, many young people, of course, training and education is a very important mission. We have specialized schools for particle physicists, covering particle physics, accelerator, instrumentation, computing. This school started in Europe, then we moved to Latin America, to Asia, and more recently also to Africa. We collaborate with school there. The first year we went to South Africa in 2010, then to Ghana, Senegal, Rwanda, Namibia, and of course one of our main goals is to build capacity and help, of course, developing countries to develop interest in science. We also have initiatives for high school students and high school teachers, a very successful, actually, teachers program that started about 20 years ago. We welcome teachers in the summer for a few weeks, and we give them a complement in physics, in experimental physics. And as you can see, we typically, over the past years, we have been receiving something like 800 to 1,000 teachers every year. And we have something like 130,000 visitors every year. Actually, we receive 300,000 requests, but we are not able to accommodate all of them. And of those visitors, more than 60% are high school students, and about 80% come from more than 700 kilometers away. So it's not just a local tourism, but people come to CERN also from far countries. And we have propagated a CERN model, CERN governance, and our values in terms of peaceful collaboration and capacity building to other institutions, for instance, to Sesame. Sesame, as you know, is the first facility in the Middle East for fundamental and applied research. It's an intergovernmental organization which is very much shaped on the CERN model and governance. And if you look at the member states, you can see that some of them are not really the best friends. They will not sit at the same table to discuss political matters, but at Sesame, they work together, again, animated by the same passion and interest in science. CERN has been involved in propagating our values and our governance and ideas for peaceful collaboration, but also in the construction of some components of the accelerator. And yesterday we had here in this room a very nice ceremony where the 2019 IIIS award in science diplomacy was given to 5 architects of Sesame, among which 2 previous CERN directors general. As I mentioned before, CERN's primary mission is science, so I'm going to talk about science in the rest of my presentation. So what we do at CERN, we study the elementary particles, among which we find the building blocks of matter, electrons and quarks, and the forces that control their behavior at the fundamental level. So we all know that matter is made of atoms, which are made of a central nucleus surrounded by a cloud of electrons, and nuclei are made of protons and neutrons, and protons and neutrons are made of even smaller constituents called the quarks. And as far as we know today, quarks and electrons are elementary particles. They cannot, elementary means they cannot be broken into smaller pieces, and they are the fundamental constituent of matters. So everything in this room, everything around us here, this gadget, myself, you, we are all made of electrons and quarks. Now, particle physics at modern accelerators, and the Large Hadron Collider at CERN is the most powerful accelerator ever built by humanity, allows us to study, to sound the matter at the level of the quarks. So on physical scale of smaller than 1 billion of a billionth of a meter. So accelerators can be viewed as giant microscopes that allows us to study not the human cells, but the matter at the smallest level of its constituents. And at the same time, the study of the very, very small allows us to understand the very big, namely the structure and evolution of the universe. We know today from cosmology and from many experimental measurements and observations that the universe had origin about 14 billion years ago from a big explosion called the Big Bang. And at the beginning it was very, very hot and very dense and essentially made of a gas of free elementary particles. That's why by studying the elementary particles and their interaction, we can understand how the early universe behaved. Then with time, the universe expanded and cooled down, and the elementary particles started to get together to first form the neutron and protons, then the nuclei, then atoms of the lightest elements, and so on and so forth, the macro structure that we see today, stars, galaxies, planets, etc. And there are essentially two complementary ways of studying the universe. One is to use telescopes on Earth or on space, and the telescopes look at the macrostructure and try to look at the farthest object to go back in time. However, there is a wall about 380,000 years after the Big Bang, beyond which the telescope cannot go. A telescope looking at the radiation really cannot look at what happened before, because at earlier epoch, the universe was so dense that light could not escape. So the pictures, the radiation map that we do of the universe today with the telescopes gives us a map at this epoch. If you want to go at earlier times, we need to use accelerators. So what do we do in practice? We accelerate two beams of particles, for instance, two beams of protons or two beams of electrons, and we at the highest achievable energies, and the achievable energy is related to the available technology, and we bring them into collisions. So accelerators are typically underground rings made of electric and magnetic fields. Complicated structure, but essentially these are electric and magnetic field. When the two protons, for instance, protons or electrons collide, several things happen. If you collide two protons, for instance, at very high energy, so very violent collision, the two protons break up into their smallest constituent. This is not scientifically rigorous, but it's to give you an idea. So in this way, we can study the constituents of the protons, the quarks, and the gluons, which keeps the quarks bound together inside the protons, and we can understand how matter behaves at the level of its fundamental constituency. Also, the energy produced in the collision can transform itself into new particles. You remember Einstein equation E equal mc squared, so energy and matter are two forms of the same quantity. And the higher the energy of the collision, the more massive the particles that we can produce. So that's why the Higgs boson has only been discovered at CERN after decades of unsuccessful hunting, because only the Large Hadron Collider had enough energy to produce the Higgs boson at detectable rates. And last but not least, the collision energy that we have now at modern accelerator, the Large Hadron Collider, corresponds to the temperature that the universe had 1/1,000,000 of a second after the Big Bang. So we are able to understand the phenomena up to that time. To study the collisions and to understand what happened, what phenomena have governed a given interaction between two protons, we use another important components, particle detectors. These are very complex and again high-tech instruments that we use to surround the collision point. They're made of layers of different technologies, and their goal is to detect essentially every single particle produced in the collision. Usually there are thousands of them, and to measure the energy, the trajectory, identify the produced particles, and to give us a picture of the collision event. So if accelerators can be assimilated to giant microscope, particle detectors can be assimilated to giant digital camera that takes pictures of the events, of the collision events. However, this camera have to work at very, very high pace, because at the LHC, the two beams of protons collide 40 million times a second. So that would be quite fast cameras. So the most powerful accelerator ever built by men and also by women is the Large Hadron Collider at CERN. So here you can see a nice aerial view of the Geneva region. On the background, the Alps, the Mont Blanc, here the Geneva Lake. The dashed white line shows the border between Switzerland on top of the screen and France on the bottom. And the yellow ring shows the location of the Large Hadron Collider. It's a 27-kilometer ring, 100-meter underground. So on top, on the surface, you don't see anything special. Operation started in 2010, and since then we have been colliding two beams of protons, which are accelerated in the two opposite directions of the ring, up to unprecedented energy. So we have been exploring a new energy frontier, about twice as large as the previous collider, which was the Tevatron at Fermilab here in the US. And these two beams collide at 4 points of the accelerator, where we have excavated 4 big underground cavern, and where we have installed 4 giant experiments called Atlas, CMS, ALICE, and LHCb. 2 years after the startup of operation, on 4 July 2012, Atlas and CMS announced the discovery of a new particle, a very special one. I will come back to this later on to explain why it's so special, the so-called Higgs boson. I would like to stress already now that the US, through the Department of Energy, National Science Foundation, and universities, and laboratories, and industry, have contributed in a very important way, a very significant way, to the 4 experiment, to the accelerator, and to the computing infrastructure. Now, the LHC required the development of new concepts and new technologies in a large number of fields. This picture, this spectacular picture, shows the underground tunnel of the Large Hadron Collider. The blue tubes are cryostats that contain new generation superconducting magnets. We have to build about 1,200 of them. They are still today the forefront of technology, at least for such a big installation. They are superconducting, and their goal, they have to produce very high magnetic field. Their goal is to keep the protons on the circular orbit, so inside the accelerator. And for that, we need very high magnetic fields, because this proton have a very high energy, and so we need high current. We are talking about 12,000, 16,000 ampere, and so you can only achieve those high currents in an effective and efficient way with superconducting materials. But superconducting materials work at low temperature, so the working temperature of the LHC magnets is 1.9 Kelvin, so about 2 degrees from absolute zero, minus 271 degrees Celsius, which actually makes of the LHC the coldest place in the universe, as we say, because I mentioned before that the universe had origin from a big explosion. At the beginning was very hot, and then it cooled down, and if you ask yourself what is the temperature of the universe today, the answer is 2.7 Kelvin. And the LHC works at 1.9 Kelvin. So we used to say that it is the coldest place of the universe and also the coolest one. The experiments are not less spectacular. Here you can see a fantastic view of Atlas, the biggest of the 4 experiments. You can see, you can appreciate the size compared to 2 human beings. The size of Atlas is half the Notre Dame Cathedral in Paris. The other experiment, CMS, contains more iron than the Eiffel Tower to stay in Paris. We, every year, each one of the 4 experiments record an amount of data the order of 10 petabyte. We have 3,000 kilometers of cables needed to bring the signal from the underground detector to the surface control room. So clearly a very technologically a very challenging adventure. Following the Higgs discovery in 2012, the Physics Nobel Prize in 2013 has been awarded to François Englert and Peter Higgs, 2 theoretical physicists that at the beginning of the 60s had foreseen the existence of the Higgs boson and had developed a theoretical mechanism that contributes to, that essentially allows us to understand what is the origin of the masses of the subatomic particles. So essentially what they have told us through their theory is that at a given time in the history of the universe, and this time is 10 to the minus 12 after the Big Bang, second after the Big Bang, something happened in the universe, and the elementary particles, some elementary particles that before that epoch were massless, like photons in this room and traveling at the speed of light, acquired a mass. And among those particles, the electrons and the quarks. So you could say, you could argue why is this important and what kind of impact does it have on our life. But actually, if the quarks and the electrons had no mass, atoms will not exist as bound states. And so, because we are made of atoms, will simply not exist. So this particle is very special because it has a very special function related to the way elementary particles acquire a mass, and so also the reason why we are here. All other elementary particles are equally important, but this one is very special, at least for me. Now, for the experts in the audience, these 2 figures shows the signals due to the production of the decay of the Higgs boson as we recorded them in Atlas and CMS in 2012, the year of the discovery. Once produced, the Higgs boson disintegrates immediately into known particles. For instance, it can decay into 4 leptons, so electrons and muons, or into photons. And what we did was to look at the mass spectrum of the decay particles in the final states. And if you look at the mass spectrum, you can see 2 nice peaks around masses of 125 GeV, which corresponds to 130 times the mass of the proton. And these peaks are due to the production of a new particle, the Higgs boson, and to its decay into known particles. Today, 6 years after the discovery, we know the mass of the Higgs boson with a precision of the per mil. We have measured the Higgs boson couplings, that is the interaction, the strength of the interaction with the heaviest particle with a precision, experimental precision of typically 10 to 30%, and we have established its quantum number. However, the Higgs boson remains largely quite a mysterious particle. I will come back to this later on, related to the most obscure part of the theoretical scenario that we know, and more detailed study of its properties are needed and will be the object of current and future facilities. So if you ask yourself, how does a Higgs boson manifest itself in a detector? What do we see? So this is an example of an event which is due to the production of a Higgs boson in the Atlas detector. So this is a transfer view, transfer cut of Atlas. You see the two proton beams coming from the accelerator from the two opposite directions. They collide in the middle of the detector, and you see they produce many, many tracks. And in these events, which has been recorded in Atlas in 20, I cannot read it, okay, you can see it. A Higgs boson has been produced, which has decayed in 4 electrons. Everybody knows what an electron is, a familiar particle. And those electrons leave signals in our instruments, in our detector. And from the configuration of the final states and from the measurements of the signals detected in our experiment, we can understand that the mother particle is a Higgs boson, is a specific event, and which is particularly background free, and determine also its mass. So this is a Higgs boson. So what's next? So I would like to mention that this is a very exciting time for particle physics, because with the discovery of the Higgs boson, we have completed the theoretical framework that describes the known elementary particles and their interaction. This framework is called Standard Model. It has been developed over 5 decades of very hard and successful theoretical and experimental work, which actually which led to several Nobel Prizes to theoretical and experimental physicists. The particles predicted by the Standard Model have all been discovered, and they are shown here. We have 6 quarks, among which the up and the down type quark, which are the fundamental constituent of the proton and the neutron, so the atomic nuclei. We have 6 leptons, which the electron, which is familiar to all of us, and the neutrinos, very intriguing particles. I will discuss that later. We have 4 particles that are responsible at the quantum level, the microscopic level, for transmitting the elementary forces, so the electromagnetic force, this is the photon, the strong force that binds the quarks together inside the neutron and the proton, this is called gluon, and the W and the Z bosons, which were also discovered at CERN, and which are responsible for the weak force, which in turn is responsible, for instance, for radioactive decays or the thermonuclear reactions in the sun. And then the Higgs boson, which, as I said before, has a very special role as the particles that gives mass. Not only that, but we have tested the Standard Model in its prediction with very high precision through a wealth of measurements, in particular at accelerators over the past 50 or 60 years or so. And the Standard Model works beautifully. We haven't seen any significant deviation from the Standard Model expectation in our measurement, except perhaps the fact that neutrinos have masses. So we could be happy. However, we are actually quite unhappy, or quite, say, puzzled, because the Standard Model is very successful, but we know that is not the ultimate theory of particle physics. The reason being that the Standard Model is not able to explain many observations and answer many open questions. And so this observation and this open question actually require new physics. New physics for us means physics beyond the Standard Model. So if you want, this excessive success of the Standard Model is very puzzling because of this reason. So here I've listed a non-exhaustive list of open questions. As I said at the beginning, the Higgs boson is a largely mysterious particle. Not only its mass is not well understood, but also is related to the most obscure part of the Standard Model. All the problems and all the question marks in the Standard Model are related to what is called the Higgs sector, so the interaction of the Higgs with for instance, with the other elementary particles. But we also don't know why do we live in a universe which is dominated by matter, with essentially no antimatter. We can produce the antimatter artificially. We do so at CERN. We have a dedicated facility. But in the universe, there is essentially no antimatter. We don't know what is the origin of the neutrino masses and oscillation. You all know about the dark universe. 95% of the universe is a question mark. It's made of 25% of dark matter, forms of matter that we don't know, and about 70% of a form of energy that is called pressure, that is called dark energy, and so on and so forth. However, in spite of all these questions, we have today no direct evidence for new particles from the LHC and other facilities. So this is the problem. So the fundamental question today is, where is this new physics in terms of energy scale? For instance, we didn't discover it yet. Is it because it sits at an energy scale which is too far to be reached from the present collider like the LHC and other facility, or is it because it interacts with the known particles in an extremely weak way, and so it requires a lot of data to be discovered? So the questions that we have seen in the previous slides are extremely compelling and extremely difficult and also intertwined. And in my opinion, they can only be successfully addressed by deploying the variety of approaches that particle physics and the nearby discipline like astroparticle physics and others have developed over the decades. Also thanks to very strong advances in accelerator, detector technology, computing, electronics, etc. And these different approaches include particle colliders like those that we have observed, but also neutrino experiments, cosmic surveys, direct and indirect searches for dark matter, measurement of rare processes, dedicated searches, and so on and so forth. And the number of projects that are needed to address all these questions and the scale also, the complexity of some of the facilities required coordination and collaboration worldwide, globally. So particle physics is becoming more and more global. We have to avoid duplication of facilities and at the same time avoid leaving gaps that are not covered. So to give you an example, for instance, one of the flagship projects in particle physics today in the US is the so-called long baseline neutrino facility, which aims at studying neutrinos, which are very elusive and also very intriguing and mysterious particles. And the long baseline neutrino facility will do so by shooting a beam of neutrinos from Fermilab in the Illinois to a detector housed in a mine in South Dakota. And while traveling from Illinois to South Dakota over a baseline of 1,300 kilometers, the neutrinos transform themselves into their different species, a phenomenon that we don't understand completely. At South Dakota, in the mine, a big detector called DUNE, an immense detector made of 4 modules of liquid argon, 17 kilotons each, will receive the neutrinos coming from Fermilab and will measure their properties. At CERN, we are building 2 prototypes of this big DUNE detector, and we are already testing one of them. And so this shows the participation of CERN and Europe in a big global project based in the US. Likewise, the US has made a very strong contribution to the Large Hadron Collider and now is also making very important participation in the high luminosity upgrade of the LHC, which consists in increasing the intensity of the proton beam so that by 2037 or so, we will be able to record an amount of data which is about a factor of 10 larger than the original LHC project. The the luminosity upgrade of the LHC, which is now being constructed, will require a modification about 1.2 kilometers of accelerators and the development of new technologies, in particular new generation superconducting magnets of different types of those that we have today in the LHC, which also are a fundamental milestone for future more powerful colliders, and we are doing so in strong partnership with the US. We are doing R&D and construction and prototyping work on this new type of magnets made based on a new material, niobium-13. And here you can see a prototype of a quadrupole built at Fermilab and being tested at Brookhaven National Lab. It's not too late to think about the next big collider after the LHC. The first discussion of the LHC took place in 1984. And operation started in 2010. So the lead time from first ideas to start of operation was about 25 years. So if you want to have a new facility by 2040, when the LHC will end its operation, we need to start to think now, and of course be driven by the physics question. So at CERN we are considering two possible projects, two options. One is a linear collider. You can see here a sketch. Called CLIC, which can collide electrons against anti-electrons, so called positron, at an energy initially of 380 GeV to study the Higgs boson and top quark in all details, and then go into higher energy, 3 TeV, with a maximum length of the tunnel of 50 kilometers. Another possibility, another option is FCC, Future Circular Collider. This will be a ring like the LHC, but 3 times bigger. So you see here the LHC tunnel, and here you see the 100-kilometer ring of a possible future circular collider. And such a infrastructure facility will allow electron-positron collision and also proton-proton collision at unprecedented energy up to 10 times larger than today at the LHC. And this facility will allow precise studies of the known particles, in particular the Higgs boson, and direct searches for new physics with unprecedented sensitivity. The technological challenges are really daunting. It will require new magnets, it will require many new technologies, but of course, again, with great potential impact on society, as we will see. Europe currently is developing its, updating its roadmap for particle physics. This is a community-based and bottom-up approach. The community gets together typically every 6-7 years to update the roadmap and to establish the priorities of the discipline in Europe, but in the worldwide context. And so we hope that the update of the European strategy, which is currently ongoing, will provide some indication about the next big collider project at CERN with the worldwide participation. I mentioned a strong collaboration between the United States and CERN. It has been a success story. The US have been participating in the main project at CERN over the decades, in particular in the Large Hadron Collider, the 4 experiment, the accelerator. And exactly 4 years ago, here in Washington, CERN and the US signed a new international cooperation agreement. You can see in this picture Energy Secretary Moniz, the director of NSF Cordova, and the previous CERN Director General Rolf Hoyer at the time of the signature. And this international cooperation agreement, on one end, emphasizes the strong collaboration over the years and also lay down the foundation for even stronger collaboration for the future based on this reciprocity principle by which Europe and CERN participates in projects here in the US and the US participates in projects in Europe. One of the questions that I get most often is, will the Higgs boson change our life? And my answer is it already has, because as already mentioned, fundamental research at CERN and in many other laboratories and all kinds of fundamental research in all fields is really a driver of innovation, because beyond the physics goal itself, it requires the development of very special, very ambitious instruments and technologies that do not exist at the time where the scientists want to do their projects. So example of application of the technologies developed at CERN cover a wide range of fields, from medical imaging to cancer therapy. So, for instance, using accelerators and producing beams of protons of light ions, like carbon ions, to bombard a tumor, which is a therapy complementary to the more common radiotherapy, because protons and light ions have the characteristic of losing their energy very locally, and therefore to be able to kill the tumor without affecting the surrounding tissues. Other examples are analysis of historical relics, solar panels, and so on and so forth. So this leads me to my conclusion on to stress the importance of fundamental research, or as Abraham Flexen a US educator, one of the founders of Princeton Institute for Advanced Studies, called it in 1939 the usefulness of useless knowledge. And this is because the progress needs revolutionary ideas and breakthroughs. Without breakthroughs, without new revolutionary ideas, progress sooner or later stagnates. And history shows that often major breakthroughs come from fundamental research. And this is simply because fundamental research is curiosity-driven and has no constraint that comes from profit or from the delivery of specific products. So it's really, free to have new ideas and any kind of blue sky initiatives. Two very nice examples that I often quote are quantum mechanics and relativity, major breakthroughs of the last century. When they were developed, they were considered useless knowledge because they were so far from any practical application. And yet, without quantum mechanics, modern electronics will not exist. And without relativity, our GPS will not work. And I would like to stress that the fathers of quantum mechanics and relativity, Einstein, Heisenberg, Planck, and many others, were not trying to invent the transistors or to invent the GPS. They were trying to understand how the universe works. But perhaps most importantly, knowledge, as the art, is among the highest expression of human beings as clever, as curious, as creative beings. And so they justify themselves by their intrinsic value. And I would like to conclude with a very nice quote by Bob Wilson, the founder of Fermi National Laboratory in Chicago, and also the first director of Fermilab. In the early 70s, he received the visit of the US Congress, and at the end of the visit, one of the congressmen asked him, "But Mr. Director, what will your lab contribute to the defense of the US?" And Bob Wilson replied, "Nothing, except making it worth defending." Thank you.
Thank you very much. We're going to continue with a little bit of discussion about whatever comes out. I'm a little overwhelmed. That was a wonderful talk. But I just have some questions that I'd like to have, we can expound on a little bit. And you really showed an impressive international scientific collaboration going on at CERN. Besides the importance, which you actually touched upon, of science diplomacy, can you say something about what that brings to the science itself, what the diversity of approaches, different countries, different backgrounds, brings to the research you do at CERN?
Thank you for the very good question. I think I can take my example. I grew up at CERN. I joined CERN in 1994 when I was a postdoc, and I grew up there. I grew up there not only as a physicist, but also as a human being. And being in an environment where you are exposed to people from all over the world really teaches you to grow up in a very open and a very tolerant way, in a very respectful way. So I think that it's not only a scientific adventure, but it's also a very good human adventure. At some point I showed a slide with the statistics of people, young people leaving the field, 90% of them, and going to other fields. And we have recently made a survey, and we have asked these people leaving the field, what are the skills they have learned at CERN that have been most useful for their current job? And of course, first of all, programming. This is very forceful. But then, working in an international environment, communication, critical thinking, but international environment and the capability of working with people from all over the world was ranked second. So that's very important for the people also.
Very interesting. Thank you. And you've been at CERN for a little bit, and in the time you've been at CERN, there have been many exciting scientific and technological advances. And I was wondering, how have you seen the support in general, financial and other kinds of support from both the member and the other countries? How has that evolved in the time you've been at CERN?
So, first of all, one thing that I think we should like to stress is that, as I mentioned, the kind of project that we do at CERN, these are really projects that span over decades. It took 25 years from the first discussion of the LHC to the start of operation, and then operation of this collider will last for another 25 years, so 50 years in total. This kind of science that really has long lead times require sustained budget and sustainable commitment. And the CERN model is so successful because of the commitment of the member states that have been, and there are those who contribute to the budget. And of course, also, thanks to the contribution of the non-member states, like the US, that do not contribute to the budget, but contribute a la carte to projects. Without that, it will be impossible, really, to realize this kind of project. And of course, I've seen strong support from the member states. I think the budget has been constant at CERN for many, many, many decades. And I think what the member states and also the other countries appreciate is CERN in all its facets, not only the fundamental research, but also the technology, the educational component and training component, which is very important, and also being an example of peaceful collaboration, which is very, very important today. We live in a fractured world, and you know, institutions like CERN, like Sesame, and a few others show really what humanity can do when we set aside our differences and we focus on common good, on common goals.
Yeah, very important. Thank you very much. And I might also add what I've noticed in my own research is that having researchers with different backgrounds really helps us crack those fundamental problems. You know, not having the same people with the same background always going at the same problem. And I found that to be very, very valuable. And I think that's also true at CERN. I have kind of a complicated question here, and some of it is self-serving, but I want to thank you how much you've mentioned superconductivity and magnets. And as we know, CERN and high energy in general are really a driver for fundamental and applied research in superconducting materials and magnet design. There are several other that I know of cross collaborations between people like me that are condensed matter quantum material scientists and higher energy physicists. And you also brought out the applications in designing new accelerators, coming out with new technologies that affect every aspect of science and technology. But I've been wondering about this, and I haven't gone there myself. If we could do more of a conversion kind of research, like together with my background in quantum materials, your background in high energy physics, think about new particles, different ways that electrons react in solids, that interact with each other in solids that we don't understand. And I've been thinking a lot about that lately. And I was wondering if you've given that much thought about putting someone like me or another condensed matter physicist on something like a Higgs, and you working on how to develop the next room temperature superconductor.
You're welcome to join.
Okay.
I'm going to hire you.
But convergent research.
No, of course, interdisciplinary and working together is very important, and not only, as I say, in a more profound way than just, using superconductivity and to build new magnets, etc. So there is more and more of that also, and I think that we have to do more in that respect. We have also an example of partnership with scientists from our discipline working with us, and our physicists going and working with them, but it's something that can be improved, and I agree with you that it's something to follow up.
I think we can put our heads together and think about how we can do that more successfully. It's been a very great ride working together, but I'd like to see more of attacking each other's fundamental questions. And I think we've had enough questions and answers now, and I just want to thank you for a truly fascinating and inspiring evening. And I want to thank you all for attending, and we look forward to seeing you tomorrow evening for the Lucy Jones plenary talk and for a preview of the 2020 annual meeting. We now invite you all to join us at the international reception sponsored by our friends at UK Research and Innovation across the street in the Palladium room at the Omni Showroom Hotel. Thank you again, Fabiola. Thank you all, and good night.